Okay, so we're going to talk about a banked curve. So if you kind of think of a racetrack where a car is at an angle, is turning the corners and going around at an angle, this would be the problem. Also, it's very much like our airplane lab, but instead of tension, we're going to have normal force. So just like our airplane lab, we had the mass F sub g, and we had tension. This time we're going to have a normal force, the force that's perpendicular to the contact surface. We're going to go ahead and draw in the vertical and horizontal components of that F sub n, and then we're going to name this as the angle. And I think in the airplane lab we had the up here as the angle, but we're going to have it down here. And it doesn't really matter, but for this particular formula, we're going to be using that theta right there. So if we go through and we take the cosine here and the sine here, and f sub g is going to equal this right here. These two will be equal. The centripetal force is going to be caused by this right here. Wow, I made that messy. That's going to be the centripetal force F sub c. So I'm taking the F sub c formula, mv squared over r. I am setting that equal to that cosine part right there. And so with all of that, and I won't go through every single little step, but what happens here is you come up with f sub n sine of theta equals mv squared over r. And we also know that f sub n cosine of theta will equal mg. So putting those together, what basically happens is the m's cancel, the f sub n cancels, this is the tangent of theta, and we end up with that same equation that we were using for the airplane lab. So it doesn't matter if it's tension or normal force, it's the same formula. So if we had a Daytona 500 racetrack with a radius of 316 meters, and we're going to bank it steeply with an angle of 31 degrees. Suppose the turns are frictionless. Okay, that would be the worst case scenario. At what speeds would the cars have to travel around them to get that? And so we would just go ahead, and the radius is 316 times 9.8 times the tangent of 31 degrees. So what would happen is they would have to take those turns at 43 meters per second. The other talk about is Newton's law of gravitation, and this is going to be where any two objects, doesn't matter what they are, attract each other. Now we're really used to having an Earth gravitational pull, but any two objects in the universe are attracted to one another. And that is the formula for the Newton's law of gravitation. And so if you have, oops, I do not know why I put that there. If you have g as our constant, g is going to equal 6.673 times 10 to the negative 11, and I'm not even sure when I get into the units. It's newtons meters squared over kilograms squared. The only reason that is the way it is so that when I multiply 2 kilograms divided by meters squared, I get newtons. Okay, so the distance with the two masses, if the masses are extremely large like a planet, we're going to use the distance between the centers of the masses. So this radius right here, we would look at the center of the Earth to the center of the moon or the sun or something like that. Now this is where, this section right here is where we get that 9.8 that we use, 9.8 meters per second squared. And we take that 9.8, we multiply it by our mass, and we get the force due to gravity. That's here on Earth. That's the radius of Earth, that's the mass of Earth in g. If we were on a different planet, we would not have a gravitational pull of 9.8 meters per second squared. It'd be something different. Multiply it by our mass, and we get our F. Another thing that's kind of interesting to think about, if you were able to fall through the Earth, because at the surface of the Earth, your acceleration is 9.8 meters per second squared. But if you were able to actually, drill a hole through Earth and fall through the Earth, you'd start at a velocity of 0, but then you would start plummeting down toward the center of the Earth. Now, at the middle of the Earth, your acceleration is actually 0. So it starts at 9.8, but because the radius is 0 right there, there is no acceleration, but you're going pretty fast. So you'd keep going, and you'd slow down, and you'd slow down, you'd slow down, and you get to this point where your velocity was 0, but again, your acceleration would be 9.8 meters per second squared. And so you could go back and forth, and if you didn't grab the edge, you'd fall back, and it would keep happening, going back and forth, back and forth. Interestingly, it takes about 45 minutes for a one-way trip, and then another 45 minutes back. And if you have a satellite will take about 90 minutes to circle the whole planet. So about 45 minutes here, 45 minutes there for a satellite. So that's kind of an interesting thing. Okay, so speaking of satellites, satellites have to move at a certain speed in order to stay in centripetal motion. So this would be where F sub c, oopsie, everything got moved over. This should be the r right there. This should be the r squared right there. Okay. And F sub c, v squared over r. F sub g is going to be our formula here. And notice that the satellite masses cancel. We don't really, I guess, care about the satellite so much, but we do care how fast it's going. It has to have a certain speed to stay in there. So when you rearrange this, what you get is the velocity here is equal to that constant g times the mass of the particular planet, Earth, divided by the radius. And now this radius, be careful of that. That's not just the radius of Earth. It will be the radius of Earth plus however far away the satellite is from Earth. You got to take that into consideration. So there's G. The mass of planet Earth is like 6 times 10 to the 24th kilograms. I'm going to divide this by the radius of Earth, but I'm going to also add in the distance to the satellite. So that is the only thing that would be different. So if you plug this all in for Earth, we have the Hubble spacecraft. I think that's the next slide, but I'm just doing it here. It's 7.56 times 10 to the third meters per second that the Hubble telescope has to move based on the distance that the Hubble spacecraft is from the surface of the Earth. So if you look at the next, you have a radius of Earth, and this is where I'm getting that additional 5,980 meters. I'm going to add that in to this to get the total R in that equation. So that's how fast it happens. The last thing we want to talk about is, well, satellites, how do they stay in orbit? Well, a satellite is just a projectile, but it's a projectile that's given enough speed so it never lands. The more speed a projectile has, the farther it goes without landing. Now, you don't want to give it too much speed because you actually are going to have an escape speed. And let's see, I don't know if I can actually pull that down. I have to look into that. But you can actually calculate the escape speed. Now, in your notes, you have a formula. V is equal to 2 times the mass of the Earth times that constant g over the radius of the Earth. Do put a square root in there. Okay, make sure you put the square root because you need that. And if you're a rocket, you want to get a rocket to escape the gravitational pull of Earth. That's how fast the rocket has to go. Okay, so a satellite's not going to go that fast because we don't want it to escape. But if you plug those numbers in, mass of Earth, radius of Earth, the gravitational constant, that's how fast a rocket would have to move. Last thing I want to talk about is why black holes, why can't light escape from a black hole? Well, if you think about the formula that we just looked at, that V is equal to 2 times m times g over r, what's happening here in a black hole is that the density is crazy, crazy high. And so what happens is the mass of the black hole is so incredibly high compared to the radius, a very tiny radius. So if you look at mathematically, you see that the escape speed would be in really, really fast. You'd have to be so fast to escape a black hole because of this formula. But you see that nothing can exceed the speed of light, 3 times 10 to the 8th. So not even light can escape a black hole. The mass of the black hole, the radius of the black hole, this escape speed is higher than the speed of light, and so not even light can escape a black hole.